because yeah, 5 minutes is over. So now yeah, I think you can see the screen. Let me go to the full screen mode and start discussing. So you have done this problem, alpha 1 sigma alpha ISI, sigma alpha ISI, that is the sound absorption coefficient multiplied by the surface area. So you have to add all those and find out the total absorption in Sabine. So there is a there is a difference between Sabine and total absorption coefficient Sabine. These two words having different spelling also. So that I have explained in the last class. And the effective absorption coefficients, that is the alpha values, are also dependent on the these frequencies that we have already seen. And we were, we were solving one problem, this one. Calculate the sound absorption and the reverberation time of a room with the following dimensions and Sabine sound absorption coefficients. That means these alpha values are in Sabine, Sabine. And when you are talking about total absorption, sound absorption, it is a Sabine with small s and no e at the end. Small s Sabine. That is the total absorption. So that quantifies in the units of Sabine the total sound absorption in a particular room. So here the dimensions are already given and you have solved this problem, and I hope you remember what was the answers. So your total sound absorption, what was the value? Total sound absorption? Can you remember? Can you open your
Sir,
notebook?
30.8 Sabine.
So it was A is total sound 30.8 Sabines. 7. Okay. And there was one reverberation time. I think that was T, which was how many seconds?
1.83 seconds.
1.83 seconds. 1.83 seconds. Now what we are doing, that now we are changing the ceiling, means the acoustic arrangements, that's what we are changing. Now the ceiling, which was made of, I think plain, what was there in the ceiling? Ceiling is a painted concrete. So we had very little absorption, 0.07, most of them were reflected. Now we are putting some acoustic tiles in it, and this acoustic tile is having a Sabine absorption coefficient equal to 0.6, which is very, very high compared to the ceiling compared to the painted concrete. So when you put paint on concrete, it becomes a reflective surface, and very little amount of sound is absorbed in the ceiling. Most of them are reflected. So now we are changing. That means we are now covering the ceiling with acoustic tiles. These acoustic tiles are having sound absorption coefficient equal to 0.6. So there is a change from 0.07 to your 0.6. We have to find out the noise reduction in dB, the change. That is, noise reduction means this will be sound, your sound absorption, there will be change from A to say A dash or something like that. So now we have to find that change in terms of dB, much like a change in noise expressed in the form of dB. So remember this figure, that now this 0.6 will be your value of alpha. Now let us first see the simple theory or theoretical part or definition part of the sound reduction or noise reduction. So this noise reduction we can use for finding out the noise reduction, we can use the following expression to approximate the reduction in SPL, sound pressure level, which is the most common indicator of noise. And we will measure this change in dB. So why there is a change? Because there is additional sound absorption materials, additional sound absorptions. So we will be measuring the change in sound absorption. Remember this, sound absorption, not sound pressure level, sound absorption in dB. This will be measuring. So how it is expressed? It is NR, noise reduction, is 10 log A0 plus AA divided by AA. That means the A0 is the original absorption present in the sub-ins, already whatever was the present values. What was the present absorption in your problem? In sub-ins?
38, 30.8.
30 point, good, 30.8 sub-ins. And now you have to find out the value of AA, added absorption sub-ins. That means whatever you have added, whatever is added to the overall absorption. So what is the change in that your absorption? So that you have to find out. When you find out that, then you use the formula A0 plus AA whole divided by the sorry, I think there is something wrong here. A0, and this will be, you have just take just like any other 10 log and find the NR value. Find the NR value. Just a minute. Oh, color is different. Anyway, doesn't matter. To find out this, I think understand this simple problem. So you have to find out this value. So now we please write down this 10 log A0 plus AA divided by A0. That will be, you have to find out where A0 is given, as you said, 10.38 or something. So that you use 30.8, you use, and find out the additional sound absorption. Additional sound absorption. That means in ceiling, we had a painted concrete of 0.07. So you must know the area of ceiling and also the change in the sound absorption coefficient, which was previously 0.07, now it is 0.6. So the change in absorption, remember that, it is the change in absorption that will be required. That means the additional absorption. Additional absorption, since you are using a material which is having more sound absorption capability. So the additional absorption is AA. Okay? Additional absorption, the difference, that is AA. Now please find out and then give your answer in the chat box. You have to do the last part only, this part. That's all, because the first part you have already solved in the last class, so it's not required. what is the change in dB? That you have to find out. So you have difficulty in doing this thing. You have not answered anyone. None of you have solved this problem. What is the problem? Tell me. Now it is coming very fast. Remember that it is change that you have to calculate. Okay. That means 0.6 dB is the new sound absorption coefficient. It was already having some sound absorption, which is 0.07. It was there. So the net sound absorption will be 0.6 minus 0.07. It will be 0.53. 0.53 will be the net sound absorption coefficient multiplied by the area. So that will be the added sound absorption. Understand? Only one student is, yeah, one student is correct. Others have made some mistake. I'm not telling which is the correct one, but one is doing Yeah, one value is perfect. Others are require some relook, revision. That means the new sound absorption coefficient is more than the previous sound absorption coefficient. So in the formula, what we have seen is the additional sound absorption. That means this value, if you want to calculate this, you have to calculate this, then you have to find out additional absorption, added absorption in Sabines. So this is 0.6 minus 0.07 multiplied by area of the ceiling. That will be added absorption in Sabines. That you put as AA, and A0 you know it is 30.8. 30.8 plus that value divided by 30.8, take a log and multiply it by 10. That's all. That will give you the answer. That will give you the answer. Let me see how now it is going on. If you have any problem in understanding, difficulty in understanding, tell me now. I'll be telling you how to solve it. Saurabh Chaudhary, or
Yes.
same. What is the area of the ceiling, Saurabh?
Yes, sir.
What is the area of the ceiling?
The 70 meters square.
So 70 into 0.6 minus 0.07. That means 0.53. 70 into 0.53. That will be your
Yes.
added absorption, AA. What is that value?
Yes. Sir, complete after adding.
No,
37.1.
37.1 is the added absorption. Okay. So now your calculation becomes 30.8 plus 37.1 divided by 30.8, isn't it?
Yes.
Calculate it. Take 10 log. So our problem was noise reduction equal to 10 log A0 plus additional sound absorption AA whole divided by A0, the original, and this is the increased value. So now we do this. So it becomes 10 log. Then your the A0 was 30.8, and now the additional absorption is 37.1. 37.1 whole divided by 30.8. What's the value now? Have you done it, Saurabh? Let's calculate this value. 30.8, additional is 37.1, add it, divide by 30.8.
3.43.
3,
Yes. Point
3 point,
43.
3.43 dB is the right answer. 3.43 dB is the right answer. Okay, now, so this part we have now Now we'll be talking about something called sound transmission loss, or STL, sound transmission loss. Or STL. So far what we have been considering, their interior treatment of the room. That means we have some, so now what is happening, you are using certain kind of materials inside materials, and changing the materials to increase the sound absorption. That means the reverberation time will be now changed. This is indoor acoustics. But what happens when sound comes from outside to inside? Then consider this, walls and other things as barriers. And this barrier is an enclosed kind of barrier. That means the receiver is inside. And sound is coming from outside. When something is coming from outside, some part is reflected. This is incident sound. This is reflected sound. And there is some amount will be absorbed. Okay, and then rest will be transmitted inside. This is sound transmitted. Okay, that means the incident sound will be modified. That means some amount will be reflected, number one, and some will be absorbed, and rest of the part will be transmitted through barrier. Okay, so the sound transmission loss, that means when the sound is moving from outside to inside, so there will be some transmission loss. That will depend on the quality of the material, type of surface texture, all these things. So if you want to have a particular transmission loss, that means absorption as a quality of the barrier, then you must use proper materials or proper surface texture outside, or the material itself, the thickness of the material, the thickness of the barrier, the material that you use as barrier. So you must know the sound transmission loss properties, sound transmission characteristics of this material. So by definition, the sound transmission loss equals to 10 log, again, the sound intensity incident and the sound intensity that is radiated from the opposite surface, that is IT. This is in dB. This is in dB. This is the sound transmission loss. So where, as we have given that STL is sound transmission loss, II where II equals to sound intensity incident on one surface of the partition in what is the unit of intensity? Saurabh?
Sir, watt per meter square.
Watt per meter square.
Water. Good, very good. Watt per meter square. Sound intensity in watt per meter square. Fine. And then the sound transmitted is the sound intensity radiated. This is the sound intensity radiated sound intensity radiated from the opposite surface. Opposite surface, okay, of the partition. Again in watt per meter square. Again in watt per meter square. That is the unit. So as we can understand from this, that so we can understand that the intensity IT, hello, হ্যাঁ বলুন, এক মিনিট আমি একটু ক্লাসটা অফ করে দিই, নাহলে শুনতে পারবো ওটা। হ্যাঁ হ্যাঁ বলুন। হ্যাঁ হ্যাঁ হ্যাঁ, আচ্ছা কটার সময় আসবো? 7টার পরে আসবো। ঠিক আছে, ঠিক আছে, ওকে। বুকিং অফিস যাবো না? আচ্ছা, ওকে, থ্যাংক ইউ। सॉरी, कुछ तो गड़बड़ होता रहता है ऑनलाइन सिस्टम में। अच्छा, so now as we can understand that the II is the sound intensity incident on one surface of the partition in watt per meter square, and from the other side IT is radiated. So which is greater? So II is the greater quantity, isn't it? So IT is less than II, isn't it? IT will be less than II, isn't it?
Yes.
Yes, sir. There will be some absorption. So it is not something, that is perfectly transparent. Perfectly transparent means acoustic transparency. The acoustic transparency is not there. So this whatever, however thin is it, so it will be transmitting some, some sound, and the rest of the things will be either reflected or it will be absorbed. So it is something like this. It comes, something goes out, and then something is passed. Whatever may be the direction, scattering or anything, and there will be certain absorption within the material. The absorption, the mechanical absorption, will be usually changed to the heat energy. So that is the thing. Now the sound transmission loss is determined experimentally for a partition between two reverberation rooms. That means we have two rooms now, two rooms from one, because that has to be monitored very closely. So we use two different adjacent rooms, and then we measure sound in both the rooms. So at one part, and in one side we create the sound and measure there also the level, sound pressure level, that is directly measurable. SPL is directly measurable. SPL is directly measured. So what happens? We measure the sound pressure level in one room, which is where the sound is created. So we have say partitioned room like this: room 1, room 2, and here we measure the measure the sound pressure level. Say SPL here, and this is, say here it is L1. L1. And the other room, these are called reverberation rooms. They are experimental and there are guidelines how to do that. And we have another SPL that we measure, and that the value is L2. Now, now what we have to find out, the sound transmission loss in terms of these measured values and some other, factors that is playing important, very important role, and rather major role here in the absorption of sound. So now the STL is modified. That was a theoretical description. Now we are giving some practical measurement oriented calculation. The sound transmission loss is L1 minus L2. L1 is greater definitely, L1 minus L2 plus 10 log S by A. S by A. Now I need to tell what is this. So L1 is the average sound pressure level time space, means particular time, at a particular time gap. So that has to be exactly same. That means you have to synchronize the measurements. That nowadays it is not an issue. If you start two clocks at different rooms, and if the clocks are already synchronized, then you can download that and then take only that part, that spectrum. That means we are having a pressure versus SPL, your pressure versus time graph, and we start somewhere and then it dies down, say like that. It goes down in one room, and other room also we have same pressure versus time, and we have a smaller, say, graph like this. So what happens, that if the clocks are this T1, this T is synchronized, then you can download it and then take a slice of this time. You take this slice. So from here you can ask, and you can just calculate the SPL for this time slice, for this synchronized time slice. So what will happen? Now let me write the entire thing properly. That L1 is the sound pressure level, but this is basically a given time space average sound pressure level, average SPL in the source room, as I have shown previously, in the source room where the sound was created. And L2 is the same time space average sound pressure level in the other room. The receiving room is the other room, receiving room. So this side was the source room, and this side was the receiving room. Okay. Now, what are the other things? Now we talk about the S. S is the total radiating surface area. Total radiating surface area. Total radiating surface area of the partition in square meter. Okay, in square meters. Say like this. So S is the total partition. So in the previous page, what we have been just a minute. Okay, so now we have the total radiating surface area in square meter. That is when you are seeing two rooms side by side, then this partition, if you see, so this is something like this. So the surface area of that barrier is S. S is the surface area. Now what is that? A. There is one more quantity, A. This is total sound absorption total sound absorption in the receiving room. In Savins. The difference L1 minus L2, this value is called the noise reduction of the partition. Noise reduction of the partition. The additional quantity 10 log S by A has been added to it because some part is absorbed within the room itself. So that quantity has been added. This is the theoretical consideration for experimental purpose. But this can be implemented in other way also. This calculation you can get details, but I'm not going to do these things today, or maybe you can just remember this formula. This formula will be available in the question paper also, or you can remember these things. It will be open book exam. You can find it out from the books also. So if the partition is now, whole thing is experimental, as we can easily find out with using this L1 minus L2 plus 10 log S by A. The STL can be easily found by measuring L1 and L2, and then you use this additional factor for finding out the sound transmission loss. Now if you know the area density, which is very important in acoustics, especially in understanding barriers, the area density is very important. Area density. Actually, if you have say particle board or partition board made of wood or thermocol or anything, or heavy particle boards, wooden boards, plywoods, anything, then if this if you know the area, just surface area, okay, surface area, say S, and if you know total weight in kg, then what happens? You need to find out the weight per unit area, kg per meter square, weight per unit area. That means that will take care of the thickness, the density, and everything. So the concept of area density has been introduced in this case, and the formula, it has been proved, it can be proved rather, that the sound transmission loss can be expressed in other ways also. Like otherwise it can be defined as 20 log WF minus 47.4. This can be examined later as to what is the proof of this total calculation for these things. But for today, let us assume these things, that the previous formula can be modified by the second one, the equation 2. Here the sound transmission loss is given as 20 log into WF minus 47.4, where W is, what is W? W is the area density. W is the area density of the barrier. Area density of the barrier in kg per meter square. kg per meter square. And what is F? What is F? What is F? Any guess? Anyone?
In meter square per kg. Or
No.
log.
F. F is frequency. This is much more detailed information. What the standards and guidelines are giving, you're prescribing, is that you have to give the specifications for finding out the sound absorption or sound transmission loss. In terms of frequency number 1. That means frequency wise distribution has to be given. That if you are, see what is happening, if I do the same experiment as I have been telling in this class today, that from the room 1 to room 2, if you are sending, and if you are sending different frequencies like F1 or F2, then F3, then you will see that for different frequencies, the sound transmission loss is different through the same barrier. The barrier thickness and other things are same, but barrier thickness and other things are same, but if you change the frequency, then you will be seeing that the changes are different. They are not constant. That means it is not only dependent on the barrier thickness, but also dependent on the frequency that is traveling. So your frequency distribution of the sound transmission loss is a characteristic curve of any barrier material. So here what we are doing, we are rewriting the formula as the sound transmission loss equals to, it is simplified, 20 log, then W is the area density. That means your kg per square meter multiplied by the frequency that you are testing minus 47.4 is the adjustment, 47.4 dB. So this is the generalized formula and commonly used formula for the calculation of the sound transmission loss through any barrier. Right. With this, I will today end this class, and I'm trying to, scan the pages of the book, and I'll be sending it to you. You can read it. There could be one numerical from this particular part: the noise reduction, sound transmission loss, and the sound absorption coefficients. There will be at least 2 questions from this entire thing. So I'll be trying to send these things today itself. Okay. Now I have to join somewhere in another meeting. So thank you very much. We'll be talking tomorrow again at 12 o'clock.
Thank you, sir.
Thank you.
Thank you, sir.
Thank you, sir. Thank you, sir.
Thank you, sir.
Thank you, sir.